Yes, our first speaker is Nicki Fairbairn. Is that Fairbairn? Yes. Okay. Nicki was born and brought up in Ayr on the west coast of Scotland. After completing her Bachelor's of Science and Master's degrees, she decided to move into the field of fundamental time-resolved chemical physics. That's cool. And joined the Headley Single Molecule Laboratory at the University of Glasgow in 2019 to study for a PhD on the time-resolved photophysics of organic semiconductors. On completion, Nicki was awarded the JSPS postdoctoral fellowship and joined the Shimizu group at the University of Electrocommunications in Tokyo in 2025 to explore the quantum behavior of organic semiconductors. She enjoys a wide variety of musical genres and frequently attends live concerts. She also enjoys long-distance running, traveling, and video games. So please welcome Nicki to the stage.
Thank you. You've bigged me up a little bit too much there. Okay, so thank you for being here for a start tonight. I'm going to basically be talking about my PhD work. So I understand that this audience might not necessarily be quantum physicists, they might not necessarily be economists, they might not necessarily be librarians, so I've kind of, when I put these slides together, I did kind of think, oh no, like, how am I going to do this? But we'll get through it, don't worry. So yeah, I've promised you laser spectroscopy, I've promised you quantum behaviour, and I've also promised you organic light-emitting materials. So let's just strip this back to the basics. So, materials, what are materials? Well, these are physical things, right? So, nothing much else to it. And of course, light emitting, it's fairly self-explanatory, right? Organic. Now, for non-chemists in the room, what does organic mean? Well, it's just a fancy word that we've given any material that's got a carbon in it, okay? So that's all it is, so don't be afraid, okay? So, the next part that I'm going to talk about is organic semiconductors. So these organic lighting materials are basically a type of organic semiconducting material, or anything under that subclass. Okay, so basically, at the core of it, energy in equals light out. Okay, light emitting material. You can also get the reverse under organic semiconducting family here. So the reverse is a light absorbing material, so light in, energy out. Straightforward enough, right? Okay, so what do these actually look like? Well, they're not far removed, thanks. They're not far removed from what you would find in your standard glow stick or, in a highlighter pen. Okay, so it's nothing crazy, but they glow really, really lovely colours. So the raw product material is basically just a powder. And what we do is we dissolve them in a solvent. Okay, so we dissolve them in, say, water or acetonitrile or IPA for any chemists that are in the room. And of course, under room light, they basically fluoresce really lovely colours. And of course, what we can do is we can put lasers into these to make them fluoresce as well. So you can actually see the laser light right here passing through our materials. So they're really lovely to work with because you get all these really, really nice colours in the lab. So what if we get these materials and we spread it really, really thin onto a metal contact? So we call it a cathode. And then we put another layer on top of that, which is our anode, okay? And that can be a transparent contact. And then we top that with a glass substrate. Well, what we've done is we've basically just made a big old organic material sandwich. And so what we then do is, as I said previously, you need energy to go in. So we can do that in the form of electricity. So we apply a current across it. And of course what we get is we get light that comes out of that, and that's a device, and congratulations, you've just made yourself your first organic light emitting diode, okay, an OLED device. So you guys might recognise OLED devices because these are very, very common in, say, big camera or in your living room, and chances are you're probably holding one right now in your pocket or in your hand. You're probably filming this using one. So these are found in smartphones very often, TVs particularly right now as well. Chances are you probably walked by one on the way here when you're walking through Shibuya, Shinjuku, wherever. Okay. So these organic light-emitting materials can be basically classified by weight. So we can classify them by weight based on the length of these molecules or the size of these molecules. And so we've got two groups. We've got small molecules, and we've also got what we call pi-conjugated polymers. What I'm going to focus on today is what my PhD research was on, which is pi-conjugated polymers. And as you can see, these are really, really, really long in comparison to smaller ones. But that allows for really, really interesting behaviour to take place as well. So of course, in the applications, the obvious one in the room is our TVs. So of course, started out with old cathode ray tubes, also invented by a Scots person. And then over time, I can't take all the credit, it was also a Russian and a French guy as well. But anyway, moving on, over time, over the last 100 years, we've basically developed this into what we now have, which is OLEDs. And of course, I could basically sit and talk about all the benefits that you get with using an OLED device over, say, a liquid crystal display. At the core of it, it's a multi-million-dollar industry. It's $50 billion, between 40 and 60 billion, apparently, according to 2025's market reviews. As lovely as that is, there are issues that come with that, right? So it's not as environmentally friendly as it could be. It's not as cost efficient as it could be. And as well, it's not as energy efficient as it could be. So that's what we're going to talk about, and that's a core focus of what my research revolves around, is how do we make these devices, such as organic LEDs, much more efficient in general. So, solution is dilution. So what we do is we use a technique called single molecule spectroscopy. So what is single molecule spectroscopy? Well, spectroscopy is basically using light to interrogate molecules. So what we do is we have a laser in most cases in the lab, and what we do is we shine it onto our material, and then we read what comes back out, and we do that using a detector. So the detectors that we use are single photon avalanche diodes for all you nerds in the room. But essentially for the scientists here, what we want to do is we want to use single molecule spectroscopy, SMS, to basically understand the material properties. So how does the chemical structure, for example, affect the optical properties of our material? Or how does the nanoscopic organisation of the material affect the macroscopic, and vice versa? So what we do is, it clues in the name, single molecule. So what we do is we just dilute our materials down loads until we have just one single molecule to look at. So this is literally what it looks like in the lab. We just dilute and dilute and dilute. So for the non-chemists in the room, let's think about this as an analogy, okay? So we have a musical ensemble here, which is our group of molecules. And if we were to isolate out one musician from our group of molecules here, which is our single saxophone playing cat in this example, what we can see is if we were to have this cat play the saxophone on its own, it'd probably do a really bad job because it's a cat. But also on top of that, what you would see is you would get random, or what you would hear, should I say, is you would hear random notes that you didn't necessarily hear before, right? So you might hear notes that were drowned out by the lion and the trumpet and the, whatever. So that's essentially what we're doing with single molecules. So hearing everything play together as an ensemble, all the molecules behaving together as an ensemble. You don't necessarily see everything that you want to see. You don't necessarily see individual behaviours of single molecules. So what does this look like in reality? Well, in reality, we do this using a microscope setup. So my entire PhD work was basically revolving around building this setup in the lab. So we have our single molecules, these green dots here, that are suspended in a clear plastic. And of course, under the microscope, these glow. So these are each individual single molecules here. We have a confocal inverted microscope, and that has a piezo scanning stage on it that allows us to scan across and generate these lovely images. And then we also have some fancy timing electronics. So that's a time to analog converter, or time tagger, whatever type of timing electronic you want to use. And then what we do is we basically drop the concentration down in the lab, and what we see is we start off with a bulk material, and then with each iteration we basically try a different spin-coated film here, and we look at it under the microscope, and we dilute and dilute and dilute until we just get individual single molecules. Okay, so as I mentioned earlier, we've got conjugated polymer chains that we look at. Okay, so these are long chains, but this is a single molecule, technically, a single polymer chain. So for the argument of this presentation, I'm just going to refer to it as a single molecule or a single chain, okay? And so it's relatively long, as you can see, and what we do is we get a laser, and we fire it 100 million times, for example, per second, at the single chain, and then we use the timing of every single photon that it emits to build up a picture of quantum behaviour. So, as you can see, or as that diagram showed, you have a laser pulse that comes in, something happens on the chain, and then a photon is emitted out. So a photon is just a packet of light, okay? And we detect that using our detectors. So what actually happens on the chain? Okay, so when the laser light actually hits the molecule, what it does is it creates a small packet of energy that wanders around the chain and hops, and maybe another laser light will come in, or another pulse of laser will come in, and it will basically generate another exton, and it will move along, back and forth along the chain, and then it will either escape as light, or it will dissipate as heat. So on the chain, this is essentially an energy loss mechanism. So a lot of the energy is lost using this process of fusion of these extons. So when, for example, two of these extons or two of these packets of light move around and crash into each other, that's known as annihilation. Okay? So exton-exton annihilation, where two extons crash into each other and only one is left moving along the chain. Okay? So the problem with that is that that directly affects this efficiency of the organic light-emitting material that's in your smartphone. Okay? So what we want to do is we essentially, on a fundamental level, is we want to understand how to control these yellow extons moving back and forth along this chain in the materials. And if we can understand this, we can try and mitigate the loss mechanisms and the losses, and we can design, and it can basically use it to infer how to design a device in the future to be much better at energy efficiency. So that could contribute potentially to organic lasers, for example, or high efficiency organic LEDs in your smartphone or in your TV, for example. So when these photons are emitted, ultimately, after the extons have moved around, they're detected by a detector. So essentially what we're doing is we're studying these molecules, a single molecule, one at a time, and we're trying to find basically really rare events that are taking place that you wouldn't normally see at high concentrations. We do that using a photon detector. Okay, so I'm going to talk to you guys about time-correlated single photon counting. So that's a bit of a mouthful, TCSPC. So essentially at the core of it, we have a pulsed laser, and we have our single molecule, and then we have our detector. And so the pulsed laser fires. When it fires, it starts a timer, and then single molecule does its thing with its extons, and then it ultimately emits out a photon, and that photon is then detected, okay? When that photon is detected, it stops the timer, okay? And then we take that value on that timer and we place it in this giant graph here, okay? So let's just think about it on a visual scale. So laser pulse fires, hits the single molecule emits a photon, timer stops, puts it into the graph, okay? Rinse and repeat, we do this over and over and over and over, okay? And in reality, what ends up happening is we build up a plot, although this doesn't seem to be working. No, okay. So essentially what it does is over time, you have a laser pulse that comes in, photon is detected, and it generates a PL decay. I wonder whether... No, it's not working. That's fine. That's what I get. That's okay. I think I'll get over it. That's fine. Okay. Okay. No worries. Just ruined the best video. Anyway, right. So we have a laser pulse that comes in. Okay. As I said before, photon is detected. And then what happens is once we do this, it builds up this PL decay, okay, and it basically looks like a giant triangle. You'll see pictures of it later, don't worry. Okay, you're not missing it. And then the next laser pulse comes in, okay. So the stream of photons that come out of this molecule when you're firing at it hundreds and billions of times a second basically gets built up into what we call a PL decay. And so that appears basically as a long decay. Okay, so photon stream, keep that one in mind. There's basically a stream of photons that come out. Okay, so we call it a PL stream. Okay, so you might be thinking, okay, well that's great, but how do you know that you're actually looking at a single molecule? Well, that's a really, really great question, because you could have molecules that are overlapping with each other under the microscope that appear to be one single molecule, but in actual fact are not. So this is where we can use our quantum aspect. So we can use some quantum techniques, we can exploit the quantum nature of light for that purpose. So you can think of light as being these packets of energy, these photons. So what we do is we basically change the detector from one detector to two detectors. So after the single molecule, we have a stream of photons that are coming out, because we're firing at it many, many times. And what we do is we have it in a 50-50 beam splitter. Okay? So we take 100% of the photons and we split it in half. So 50% of the photons are going to detector 1, 50% of the photons are going to detector 2. And this is called a Hanbury, Brown and Twist optical scheme. Okay, so instead of timing when the photons arrive, we're actually going to start counting them now. So in reality, oh, this one worked. Oh, wonderful. Okay, I'll have to squeaky bum time for a second there. Right, okay. So we have our photons that are coming out, and of course, some of them are getting reflected into this detector, detector number 1. Some of them are getting transmitted into detector 2. What we do is when there's a simultaneous count on both of them, as in a detection on this detector and a detection on this detector at the same time, would that happen? No, right? Because you can't split a photon in half, okay? But what we can do is we can do some clever timing electronics to actually force that to happen. So when that does happen, we call it a coincidence occurrence. This is where the hard part comes in. I hate explaining this. It's just so hard. Okay, so let's think about it in terms of what does the actual detector see. So let's think about after the 50% split on the beam splitter here, what does this detector see and what does this detector see? Okay, so this detector basically sees a laser pulse and then a photon coming off of the single molecule. A laser pulse, maybe nothing, laser pulse, photon, laser pulse, and so on and so forth, okay? This detector sees the same thing, but because you can't split a photon in half in this case, you're never going to get a situation where a photon is detected within the same time frame, okay, between laser pulses. It just won't happen, okay? And the whole point of us doing this is basically to test whether or not the single molecule that we're looking at can only emit one photon at a time, okay? So then, how is that going to help us? Well, what we can do is we can basically take this gap, this time window between the detectors, and shift one of them with respect to the other, okay, by one time window, like so, okay? So we're basically falsely aligning them using our time lapse. So we see that this photon here now aligns with this photon with respect to the time between the laser pulses, and again here, so that's 2 counts. This might continue on off the screen, for example. See how many times that happens and say, okay, cool, that was a +1 time lag between laser pulses here. So let's plot that into what we call our histogram. We can do that in one direction, but we can also do that in another direction as well. Okay, we do the exact same thing, but this time it's in the negative direction with respect to detector 1, and we plot this as well. Okay, so then we just do this over and over again with various lags with respect to the laser, and what we do is we generate what we call a photon anti-bunching histogram. Okay, that's wonderful, really, really pretty. Okay, so these are basically these coincidence occurrences at different time lag values. So if you're sitting there like, WTF, like why did I come out here on a Friday night? God, I could be anywhere but here. Well, that's okay, right? So I'm just going to dumb it down to you. So essentially, what we care about, somebody's got it. Okay, it's cracked it. So essentially, all we really care about here, okay, at the core, if you sat for the last 10 minutes and you're like, I don't know what's going on, that's fine, right? All we care about here is the depth of this dip, right? That's all we care about, okay? What this tells us, using some fancy mathematics, is that the depth of the dip tells us exactly how many extons are active on the chain at once, and the shallower the dip, the more extons there are, okay? So these conclusions are only possible with single molecule spectroscopy because we're exploiting the quantum nature of light and we're measuring discrete emission of single photons. So that says, okay, cool, this molecule we're looking at has 1 exton on it, or 2 extons, or 4 extons. So remember when I promised you a triangle earlier? Well, now you've got your triangle. So it's pretty disappointing, really. But what this tells us, basically, or what we've done is we've basically generated our photon anti-bunching histogram, our fancy dip on the previous slide. But this is over the duration of the time between laser pulses. Okay, and this is just a probability of a photon arriving, right? So we've done it on average across the whole excited state lifetime, the PL, okay? That's great, but it doesn't really tell us much other than there's probably an exton somewhere in the molecule. So what we can then do is we can instead time resolve that further. So we can take our excited state lifetime here, between the laser pulses, and we can split that up even further. So we're going to do that just now. No, we're not. Here we go. Okay, so we've got our 6 slices here. 1, 2, 3, 4. Yeah, I can count. Great. Okay. But what we can do is we can basically perform what we call time-resolved anti-bunching, which is a relatively novel technique. It's only been developed in the last couple of years. And what we've done basically now is extracted our photon anti-bunching histograms, and this text is just for anybody that might be within the field that understands what's going on. More than I do, certainly. But basically what we've done is we've taken our photon anti-bunching histogram and we've sliced it up along the excited state. And again, if you're sitting there like, still don't get what's going on, don't know what's going on here, basically what you can see is this dip, this reduction in the dip throughout the excited state lifetime, okay? Now, what that's telling us is that we're able to measure with extreme sensitivity that the excitons that are moving along our single molecule are crashing into each other, and we can measure the rate of that. So in the paper from my PhD work, basically we were able to tell that the number of excitons that were moving around the single polymer chain that we were looking at went from 4 excitons to 2 excitons to 1 excitons. And we're able to measure that with extreme sensitivity, and we're able to measure that basically within about, it was over the course of about 1,000 trillionth of a second. Okay, so we were doing that just with fancy lasers and timing electronics. So what that also told us was that the rare events that were occurring on the single polymer chain was taking place, it's only 35 rare events per million. Okay, so we were able to measure that, which is pretty crazy when you think about it. So ultimately, this annihilation that we're measuring, so that is basically a fingerprint of the annihilation taking place on our polymer chain, which is what's causing your smartphones to suck, right, or not last very long. Basically, what we can do is we can work out ways of trying to reduce that. So we can, if we can again understand what's causing that, we can try and reduce it and make your phones last longer, essentially. So with respect to that, for example, chain conformation effects, so the shape of the polymer, or the molecule, and how it's physically orientated in space, that can affect how easily your excitons crash into each other, and therefore how much loss there is on your material. And therefore, if you understand why that's happening, you can therefore say, okay, well, why don't I stretch out this chain instead? That way the excitons are not crashing into each other, and that way the molecule's going to last longer in terms of the light that's emitted from it. So what that means is it means you can basically exploit this for brighter organic LEDs. You can use it for example, organic light-absorbing materials, which I mentioned at the very beginning of this talk. So for your solar panels on the roof of your house, how to make them more energy efficient, development of organic lasers as well, and also we've got a new tool here. So time-resolved anti-bunching, yeah, okay, we've done it with organic semiconducting materials, but can we apply it to anything else? Who knows? So I think with that, we can, now that we've basically established that the technique of annihilation can be measured with such sensitivity, can we design better molecules, or molecules that are better at not losing light over a specific amount of time for us to put into our smartphones? So can the fundamental design of these molecules be kind of exploited in a way to make your technology last longer in terms of brightness and your screen not dying over time? On top of that as well, time-resolved anti-bunching can be used for other materials as well. So you could do it for bioimaging or medical applications. That's probably a bit of a stretch, but is there other stuff that we could apply this technique to? Yes. And then as well, the kind of hot topic at the moment, I know that there's a lot of quantum physicists in this room, but can we use entangled photon pairs to develop new, very novel techniques such as like quantum spectroscopy, which is definitely something that I'm focusing on at the moment. So I don't really have the time to get into this, and I did promise you more quantum, but I'm more than happy to chat about this over a drink later at the bar, because I think it's a really, really interesting region, an area of the field that I would like to talk more about, which is instead of using just a single photon to excite, can we use fancy optical orientations to infer other interesting information using entangled photon pairs? So that's, I guess, the quantum optics aspect of it. So I think I've rambled along long enough for this, so I'm going to shut up. But thank you for having me, and thank you for listening to my talk. And I hope you enjoyed it, if anything. And next up we have Stefan Lejeune as well.
Yeah, hi, thank you for your presentation. I'm thinking of recent research around the Casimir effect, and the existence of virtual particles. And if you were to refine this further, would you get to a point where virtual particles would actually create like anomalies in the imaging of monitors?
That is a very good question. I guess that's potentially a research direction that you could go in, yeah. So time-resolved anti-bunching is a really, really new technique, as in it was only really first established in, I think, just prior to COVID is when the first, like, I don't know, this is feedback. I think time-resolved anti-bunching certainly is a relatively new technique, so there's only one group that's ever developed it and used it, and I think there's only 3 publications on it. In fact, no, I lie, it's 2 groups. So I think that's a really good question that I can't really answer based on current publications, but I guess, yeah, you could. I don't know how you would do that, but there's definitely research direction there. Nobody's tried it, essentially. I don't know whether that answers your question. That's a really good question. Oh no. This is a hard question.
No, these are easy questions. And no, I'm not a quantum physicist, I'm an engineer. So, but this is very cool work. Sounds like a lot of fun. And yeah, let's talk about the entangled photon sources sometime. But I want to ask just a simple question about your photons and your molecules.
Yeah.
What temperature do you have to do these experiments at? And do the photons come out in a particular direction, or do they come out in all directions at random when they come out of when they're emitted?
That's a really good question. So, right, I'll basically attack question number 1 first, which was, what was question number 1?
Temperature.
Room temp. So everything's done at room temperature. So that's a really nice thing about it, is that the samples, because you're diluting everything down a ton, 1 times 10 to the negative 6 meg per mil, which is nothing. You're barely using any material sample, so the organic chemists love you because you're not wasting their materials. But the other nice thing about it is that, provided it's not a really high maintenance sample that requires, a vacuum or requires, no oxygen getting to it or anything like that, most of them are room temp. Although this begs another question, which is what you can do is you can use essentially I don't know if you've heard of attotubes or cryogenic measurements, attotubes, cryogenic measurements basically to observe the exciton at lower temperatures for other diffusion measurements as well. Yeah. But for all the work that I did, it was super low maintenance in terms of temperature. It was just all room temperature measurements. The only issue was the materials needed to be made in a nitrogen purged glove box. And when they were being measured, they were measured under a nitrogen purged sample chamber. But yeah, they were really low maintenance, really nice measurements to make. And question number 2, yeah, so we used a confocal microscope. Is anyone a confocal microscopist? Just thought I was, okay, this guy, cool. Yeah, so basically what you're doing when you're using a confocal microscope, you're using a pinhole, and you have a Gaussian detection volume, which is basically an hourglass, essentially, shape when you're exciting your sample. And these samples are usually about 100 nanometers thickness, give or take. So when you're exciting your sample, you're scanning across your sample and you're generating a map of where all the single molecules are. And then you're moving your laser back onto a single molecule and basically blasting the hell out of it. And then the PL that comes out of those, the photoluminescence that comes out of those single molecules.
Tilting the microphone at the speaker that's causing the feedback.
The PL that comes out of the photons are basically collected using an epifluorescence setup. So basically, redshifted PL comes out of the material into a dichroic mirror and then directed either by fiber or just by free space optics into the detector. But what we do is we use a really tight focus lens in front of the SPAD if we're doing free space optics for the purposes of collecting as much as we can on a 100 micron sensor array. Yeah. Does that answer your question?
Mostly.
Cool. Mostly. Okay, we can chat. Cool.
So, there you go.
Okay.
Thank you.
Hello.
I also have 2 questions. So
Yes.
curious about the materials that you've been studying, and also the efficiency gain potential if you were getting to full efficiency.
Yeah. So, okay. What would you like to know about the materials? Anything? Or
What
just-
excites you the most about the material?
What excites you the most? The colors, actually. The colors are really nice, I would say. Some of the colors are really nice to work with. It just adds a kind of nice aspect to your work because you're like, at least I'm doing something that looks pretty, I guess. We have this thing in the lab, or I think it's now a viral thing, it's kind of Fluorescence Friday, where you take a picture of your fancy samples, essentially. I would say the colors, but yeah, essentially these are polymer chains are what I kind of focus on, but you can do small molecule measurements on the smaller category of organic semiconductor materials, which I don't really, it's cool, but I think polymers are more exciting because you can get multiple chromophores on a chain, or multiple emitting sites on a chain, so they do cooler stuff. On top of that as well, you've got these chains that can coil up, or you can add a chemical to force them to spread out, and if you that's kind of what a lot of this is dedicated towards, is using a specific solvent that can get your molecule to behave in a way that's beneficial for your application, then that's great, Question number 2. What was question number 2?
The efficiency potential.
Efficiency. Yeah, so this is a tricky one. So I don't know if there's any organic chemists in the room, but basically there's a technique that you can use to try and enhance the efficiency called light harvesting. But basically, due to the rules of chemistry and physics, the efficiency hits a ceiling at 25%. And so you can use a technique like light harvesting to try and... you can use basically a technique called light harvesting basically to try and get more and push more out of that 25%, but it's a very complicated thing to do. So already your devices are capped at that, annoyingly. That's done something weird. I didn't touch it. Still throw me out. But yeah, over every publication, for example, that comes out every year is some group somewhere that have basically tried and probably used machine learning to come up with a range of viable molecular structures that might improve your efficiency of your material. And so usually every year there's a publication that comes out that says, we got from 10% to 11% for this very specific molecule that's never going to get put into the device. So yeah.
Thank you.
Thank you so much. I know your motivation or the interest was more to enhance the efficiency, but due to the directional nature of these polymers, if I may ask, is there a possibility that we actually try to push, like I'm assuming the lower efficiency is basically the excitons basically dissipating the energy in form of heat.
Mm-hmm.
Would it be possible to use molecules like this to make directional transport of heat, to exploit the excitons in such a way that we are directionally dissipating them in a specific direction?
When you see directionally dissipating,
For example,
Yeah,
when
elaborate.
excitons are basically getting dissipated in a certain direction rather than being dissipated. Once the exciton dissipates, or
Microphone to your mouth, please. We can't hear you.
in my mouth, I'm assuming the energy basically dissipates omnidirectionally, like it goes in all the directions when the exciton collides with another exciton. Or there's a directionality to it already.
so that energy is, so they crash into each other, and then essentially that energy is dissipated as light, which is the photon that we're detecting.
Okay.
Yeah. But what you can do as well is, if after a period of time they're basically rolling back and forth along the chain,
Mm-hmm.
and they might just run out of puff, basically, where they just run out of they just dissipate and they're lost as thermal dispersion, basically. Yeah.
Okay.
Which is why the cryogenic measurements are really interesting, because if you cool everything down, you can observe this like kind of it's called frustrated transport of exciton fusion, where the cold atmosphere can affect like how the thermal dissipation takes place and things like that. Yeah.
All right. Okay. I think I might have misunderstood.
No, that's my
Thank you.
fault, man.
No, thank you.
Hey, you got a question here? There you go.
How pretty are the pretty colors?
Very pretty.
Yeah, what I really wanted to ask is, can you get IR and UV out of these things as well?
Yes, you can.
Wow, that's very pretty.
Yeah. You can if you hook up like an SNSPD or something, then yeah, or like are you in the field? Are you in the field? Are you in the?
I don't have a master's degree in material science.
Oh, well, basically we can, if you attach an IR detector, you can detect IR, or it can be, more IR than UV. It really depends on what wavelength you're exciting with, but typically energy loss results in a shift of wavelength to the red, which is more to the red IR, and thereon, yeah.
I'd like to ask about the simulation. Do you use the simulation, and has any of your results contradicted with the simulation?
Simulation with respect to?
To exciting it and trying to predict how many excitons there are going to be and how many annihilations going to be?
Yeah, no, that's a really good point. So I've never done any simulations for this. There are theoreticians that do that, but I'm strictly an experimental physicist. I do know, I think, that's probably a good question actually. You could probably use, or I don't know, there's probably someone out there that's using simulations with AI for trying to predict how an exciton will move. But unfortunately the problem with this is the random nature of the energy diffusion, right? So this comes back down to the random walk, which is you don't know how it's going to behave, so it's very, very difficult to predict. But you could probably use a simulation to work up a kind of library of behaviours, I guess. But yeah, I'm a lowly experimentalist. I'm not clever enough to be a theoretician or a simulation.
Okay, I have two boring questions. One, with the confocal microscopy, you cannot resolve single molecules, so you are doing some mathematical thing.
No, you can.
Really?
Yeah.
You are not using STED or?
We're not using STEM, we're just using a really, really high numerical aperture on the objective.
I see.
And very often as well, so of course you're at the diffraction limit.
Yes.
You're well beyond the
Of course.
diffraction limit, right? Yeah. But first things first, these single polymer chains are very, very long. But yeah, we're
Longer
not.
than the diffraction limit.
Sorry?
Yes, they are big enough.
They are partially that, yeah. But you're right on the diffraction limit.
Okay,
Yeah.
my second, maybe less boring question is about the light in, energy out materials. Is your research going to improve light in energy out?
So yeah, that's a really good question. So very often these materials, the organic light-emitting materials, can often be blended, and they're known as polymer blends with other materials and doped and things like that for applications in.
Because we are very far away from the photosynthesis in terms of energy output, right?
Yeah. Well, ask me about entangled photons. But no, the light-emitting materials can be blended in things, they're called polymer blends. And very often the mechanism in which the organic LEDs lose, let me think about this, the loss mechanisms apply also to light-absorbing materials, such as organic photovoltaics or organic solar cells. So it doesn't matter whether the energy is going in and light's coming out, or light's going in and energy is going out. It helps both causes, basically. Yeah.
Thank you very much.